Proving sums with mathematical induction. So we're going to jump straight to an example. Let's have a look at, we want to prove by induction that the sum from k equals 1 to n of k squared equals n times n plus 1 times 2n plus 1 all over 6. For all positive integers n, so that's for n is greater than or equal to 1. So sometimes it helps to just write out, to change the sigma notation into expanded form just to see what's going on. So we start off with k equals 1, so we have 1 squared, then we keep increasing k by 1, so we got 2 squared, 3 squared, 3 squared, and we keep going until we get to n squared, and we need to show that that's equal to n times n plus 1 times 2n plus 1 all over 6. Now, if we're going to prove it with mathematical induction, we need to show it's true for the base case, and the lowest value of n we can take is 1. So we're going to prove that it's true for n equals 1. So if we have n equals 1, we've only got one term on the left-hand side. So we've just got our 1 squared. And does it equal the right-hand side when n equals 1? So we have 1 outside of 1 plus 1, outside of 2 times 1 plus 1, all over 6. So we get 1 squared is 1. Then we get 1 times 2 times 3 over 6, which is just 6 over 6, which equals 1. So it's true when n equals 1. Then we're going to assume that it's true for n equals k. So we're going to have 1 squared plus 2 squared plus 3 squared all the way up into k squared equaling k outside of k plus 1 times 2k plus 1 all over 6. So we're assuming it's true for n equals k. Now we need to prove that it's true for n equals k plus 1. So we're going to get 1 squared plus 2 squared plus 3 squared. And always when we're proving a sum true for n equals k plus 1, we like to write the term before, which will just be k squared, plus our last term now of k plus 1 all squared. And we're going to substitute n equals k plus 1 for n. So we're going to get k plus 1 times k plus 1 plus 1 times 2 outside of k plus 1 plus 1 all over 6. Now, we know that all the way from 1 squared to k squared, we have this. So we can go ahead and sub that in. So we're going to sub it in for all of this part here. So all of that we know is equal to k outside of k plus 1 times 2k plus 1 all over 6 plus k plus 1 all squared. And we'll tidy up our right-hand side. So we want to show that it equals k plus 1 times k plus 2. Expanding that last bracket, we're going to get 2k plus 2 when we look at this. And then 2 plus this one is going to give us plus 3. And we want to show if that left-hand side does in fact equal that. So let's just take our left-hand side and we're going to multiply our second term by 6 over 6. So we get a common denominator. So we can go ahead and just add our numerators. So we're going to get k times k plus 1 times 2k plus 1 plus 6 times k plus 1 squared all over 6. Now we can factorize out a k plus 1. And that's going to leave us with k times 2k plus 1 plus 6 outside of k plus 1 all over 6. Then let's expand this bracket on the inside. So we're going to get 2k squared plus k plus 6k plus 6 all over 6. Tidy this up. Get k plus 1 times 2k squared plus 7k plus 6 all over 6. And let's see if we can factorize that quadratic inside the bracket and make it a bit nicer. So we'll just do that over here. So because we have 2k squared, non-monic, let's go ahead and times just write it down. So we've got 2k squared plus 7k plus 6. So it's times the 2 and the 6 and get 12. So we'll write out 2k, all over 2. And we're looking for two numbers that multiply to positive 12 and add up to 7. So we're going to get positive 4 and positive 3. We can factorize a 2 out of this bracket and get k plus 2 outside of 2k plus 3 all over 2. And those 2's will cancel. And that's what we can factorize our quadratic as. So this equals k plus 1 outside of k plus 2 outside of 2k plus 3 all over 6, which does equal our right-hand side. And now we've successfully proved that the statement has to be true, because if we assumed it true for n equals k and proved true for n equals k plus 1, it's true for all values of n that are greater than or equal to 1. So it's therefore true by mathematical induction.